Good day. Today I will introduce you to a spreadsheet program used for design of reinforced concrete structural elements. It is named RCC 11 Element Design. This spreadsheet program designs to Eurocode 2, and as I said earlier, it can be used to design structural elements of slab, beams, and columns. It is a public release version, and I will provide a download link to the file in the video's description. In this video, I will demonstrate the use of this spreadsheet program for slab design. First of all, let me explain some important parameters in this spreadsheet program. When we look at the input section, data is entered in blue cells only. Similarly here, anywhere the cell is blue, you can change data or enter data. Now let's take a look at the meaning of some of the parameters in the input section. First of all, we see location. This is where you input the name of the floor you are designing. M here stands for design moment. This symbol here stands for redistribution factor. Span in millimeters. Height or thickness of the slab. Bar size, reinforcement bar size, which here is 10. Cover to reinforcement, which in this example is 30. FCK, the characteristic cylinder strength of concrete, which is 30. It can be changed here. And then FYK, the characteristic strength of steel. We have GK, which stands for the dead weight of the slab, and QK, which stands for the live load of the slab. This YC and YS are the factor of safety for the concrete and steel respectively. So now let's explain some important parameters in the output section. The D here stands for effective depth. This is the distance from the top of the slab to the center of the steel. X here stands for neutral axis depth, which shows how much of the slab is in compression. X over D limit is a safety ratio, usually 0.448, that ensures the slab fails gracefully rather than suddenly. We have Z, which is lever arm, which is the internal distance between the center of compression and the center of tension. AS, which is the area of steel required. As you can see in this case, it is 532 millimeters squared per meter. AS minimum, the minimum steel required by code to prevent brittle cracking. And this is the provided steel, which is 628 millimeters squared per meter, which must always be greater than the steel required. Then around this area, we have the deflection check. It's also calculated here, and you can also view it here. In this case, for this design, it states it's okay. Now look at actual L over D. That is the actual stiffness of the slab. Permissible L over D is the maximum allowed bendiness. Then here we have the modification factor, which is a multiplier used to adjust the allowable span to depth ratio based on how much extra steel that was provided. So in any way, the software, you can see all the calculations and how it derives their figures. You can see the area of steel required, the area of steel provided, and deflection checks. Now moving further to the right, we can select the type of slab we are designing. Here we have simply supported. This is end span, interior span, cantilever, and support. In this case, we leave it as simply supported. Here we could change the characteristic cylinder strength of concrete. So once it's updated here, for instance, let's say we take 25, you see it's updated here. We can select the usage of the slab. We have dwelling, we have office store, we have parking. So in this case, we leave it in dwelling. Moving over here, we have the bar area, which is 79, which is the area of a reinforcing steel of 10 millimeters. Now let's take a look at this section. We have the bar area, which states 79. So this is the cross-sectional area of a single bar. So this 79 is for a reinforcing bar size of 10 millimeter diameter. We have this N. N is the factored load, which is based on your GK and your QK. And we have the FCK 25, which is the characteristic strength of steel. We have the depth, effective depth. We see the X over D limit, actual X over D. So the X over D limit, as I said earlier, is an Eurocode safety constant. Then we have the Z. We have X, which is the neutral axis depth, and some other things as you can see here, which we have discussed some of them in the output section here. Now, when we go over to this table, you look at the checks. For the design to be valid, all this must remain as 0. So once it is greater or less than 0, then there's something wrong with the design and you need to check it out. So here, deflection is satisfied, section is satisfied, cover is satisfied, and maximum spacing of reinforcement steel is also satisfied. Now, this is just a summary of the important parameters we can care about. I will later on do a detailed video on all the parameters and what they mean later on in this tutorial series. So now we are going to test this spreadsheet program by treating a worked example from a well-known textbook and then comparing the results. The name of the textbook and where you can get it will be provided in the video's description. So now let's use the spreadsheet program to treat this example and see whether the answers we get from the spreadsheet program is similar to what was obtained in this example. Now let's take a look at the example. It's design of a one-way spanning floor to Eurocode 2. And it says, design the floor shown in figure 8.27 for an imposed load of 4 kN per millimeter squared, assuming the following material strength: FCK 30 Newton per millimeter squared and FYK is 500 Newton per millimeter squared. Now the environmental conditions fall within exposure class XC1. Now these are the calculations. So now let's enter the parameters into the spreadsheet program. For this spreadsheet program, you have to calculate the design moment of the slab on your own. Once you have gotten the factored load, you just use the required formula to calculate the design moment. Now let's go back to the textbook and see. Let's enter as much parameters as possible. Now there's an imposed load of 4 kN per millimeter squared, which is here. This is the imposed loading. And then we have FCK, which is 30, and FYK, which is 500. So let's change this FCK to 30, and then FYK is already in 500. Now the span is 4650 millimeters. So this is the span. Let's leave this redistribution factor like this. Now the overall thickness of the slab was determined to be 185 millimeters. So we input that into the spreadsheet program, and then the exposure class XC1 15. So that means the nominal cover to reinforcement is 25. So we input that 25 here as cover. Now the diameter of the main steel is assumed to be 10 millimeters. So which is here. So let's look at the design moment. Now from the example we could see that the self weight of the slab is 4.625 kilonewton per meter squared. So we input that. It's called permanent loading and it's summarized here as 4.63. So what we are doing is, as much as possible, get the parameters from the textbook and put it here and see if we get almost the same result or the same result as in the area of steel required and the area of steel provided. Now let's look at the calculated moments. So the calculated moment for this design is 33.1 kilonewton meter. And so here it is. Now let's compare the answers from this spreadsheet program to that obtained in the textbook. D is the effective depth. It was assumed to be 155 millimeters. And here in the spreadsheet program, that was what was calculated exactly. Now let's take a look at the lever arm, Z. The lever arm here is 148.4. The one from the textbook is 1 47.3. The answers are very close. Now look at the area of steel required, which is 517 millimeter squared. Now comparing it to the one from the spreadsheet program is 513. So the answers are similar. Now let's look at the area of steel provided. That is T10 at 150, which is 524 millimeter squared per meter, which is the area of steel provided here, H10 at 150 centers. That is area of steel 523. So the answer is similar. And all serviceability checks are satisfied. So you can see that the spreadsheet program is very, very reliable. Next, I will demonstrate how to use this spreadsheet program to design a slab panel from a real project. Now, this is a first floor slab panel arrangement for a real life project. You could see the panels, and I'll be designing this panel very quickly using the spreadsheet program. We are assuming some parameters for this. For instance, for the strength of concrete, I will take it as 25, and steel, I'll take it as 460. And then we can see the span of the slab is 2,630 millimeters. We input that into the spreadsheet program. I will demonstrate to you how quickly we can analyze this slab. So now FCK, let's leave it at 25, FYK 460. Then the live load, let's give it at 4. Now the dead weight will be calculated using the unit weight of concrete. So I will be assuming the thickness of the slab. Let's start with say 170. Okay. Then the bar, the reinforcement bar size, let's make it 12 mm. Concrete cover 30. Then the span is here 2,630 millimeters, 2,630. The redistribution factor, we'll leave it as 1. Before we find the design moment, we need to quickly calculate dead weight or the permanent load. So to do that, we multiply the thickness of the concrete by the unit weight of concrete. So the thickness of the concrete here is 170 millimeters, which is equivalent to 0.17 meters. And then we'll multiply it by 24 kilonewton per meter cubic to find the value here. So we'll bring up the calculator. So now 0.17 times 24, and then we get 4.08 kilonewton per meter squared. So let's add 1 kilonewton per meter squared for finishing, plus 1. We get 5.08 kilonewton per meter squared. So we input that here, 5.08. So now looking here, this n here is the factored load using these two values. This value is what will be used to calculate this design moment. So we analyze the slab as simply supported and use the formula for design moment. The formula is WL squared over 8. W stands for this value n, L stands for the span of the slab, and then everything divides by 8. So let's do that quickly using our calculator. We enter a bracket. W, which is equal to the value of this n, that's 12.858 times 2.63 squared. And close the bracket, and we divide it by 8, which gives us 11.11 or 11.12. We write it here, 11.12. Okay, that's a very small moment. Immediately we see it said section fails on maximum spacing because the area provided is T12 at 525, which is way above the maximum spacing allowed by code. So you can see here, confirms fail in maximum spacing. So what you can do in this case is to reduce the bar size to 10. You can see now that the maximum spacing error is no longer there. It says provide T10 at 350 center to center. You can see how quickly we can use this spreadsheet program to quickly analyze a slab panel. You can try a lot of things to come out with what you feel is economic for your design. We could even reduce this thickness. Let's reduce to 150 and see what we get. You see that everything still passed the test, which means that instead of using an overall slab thickness of 170, we can actually reduce it to 150, which will save a lot of cost. Now, looking at our design again, we have area of steel calculated as 249 and area of steel provided as 262. That's T10 at 300. For this type of slab with a very small moment, we can actually use a reinforcing bar size of 10. So you can see all deflection checks are okay and there are no error messages here. So this is how you can analyze slab panels. More videos on how to analyze different types of slab panels will be coming soon. Thanks for watching this video. Please support this channel by subscribing to our videos. Have a nice day.